Okay, thank you very much. Well, this talk is not exactly about low-dimensional dynamics, but it's about cohomological aspects of cocycles taking values in group of diffeomorphisms of low-dimensional manifolds. So let's start fixing our setting. For the time being, our dynamical system will be an arbitrary homeomorphism on a compact metric space. And we'll consider a topological group, or more precisely, a metric group. I mean a group where the topology is induced by a distance. And the fundamental objects in cohomological dynamics are cocycles. In the case of dynamical systems given by homeomorphisms, by just a map, I mean, a cocycle is nothing but a map, in our case a continuous map, from the metric space to the group. And of course, when we are thinking about cocycles, we are thinking about Birkhoff products or Birkhoff sums, depending on the notations that you use for the operation of the group. So we will use this notation for Birkhoff products. And within the family of cocycles over a homeomorphism, there is a particular class which are in certain way the trivial cocycles of the system, which are those cocycles that can be written in this way. And that means that when you consider the Birkhoff product, this Birkhoff product only depends on the initial and the final points of the orbit segment. Okay? And so this, as I said before, this should be considered as the trivial cocycles of the map. And well, in dynamics, cocycles appear very naturally in different contexts. And in fact, the problem of determining if certain cocycles are or not coboundaries, it's also a very natural problem, because many problems in dynamics can be reduced to determine if certain cocycles are coboundaries. So it's a rather natural problem to try to characterize coboundaries of dynamical systems. Okay, and in this talk we'll concentrate on cohomological aspects of hyperbolic systems. So to define what a hyperbolic homeomorphism is, let's introduce this very classical notation. For positive epsilon, we'll define the local stable set in this way, as the set of points that for the future are at distance less than epsilon to the orbit of X. And of course, the unstable in the usual, you define the unstable set in the usual way. And we use those sets to define what a hyperbolic homeomorphism is. That means that points on the local stable set approach exponentially fast, and on the unstable set they separate exponentially fast. And also we will assume that the space has local product structure, the homeomorphism, sorry, has local product structure. That means that the local stable and unstable set intersect in just a point, provided X and Y are sufficiently close. Okay? Typical example of hyperbolic homeomorphisms are annals of diffeomorphisms, or the restriction of diffeomorphisms to basic pieces of axiomatic diffeomorphisms, or even subshift of finite type, are all examples of hyperbolic homeomorphisms. For us, all hyperbolic homeomorphism will be assumed to be transitive. Okay, this is just a matter of to simplify the exposition. Okay, and well, we are interested in understanding to try to characterize the coboundaries of hyperbolic homeomorphisms for different groups G. Okay, As you can see in the title of the talk, we're mainly interested in the case where G is a group of diffeomorphism of a certain manifold. In our case, will be the circle. That manifold will be the circle or surfaces. And we try to understand, to characterize those coboundaries. Okay? That means we have a cocycle, and we want to know if this equation, which is usually called the cohomological equation, admits a solution, where phi is the data and u is the unknown of the equation. Okay? So we are trying to find dynamical properties to guarantee that such an equation has, in fact, a solution. Okay? So going back here, so we are trying to, first of all, we are trying to find necessary conditions to guarantee that a cocycle is a coboundary. And the first condition is the so-called periodic orbit obstructions. Of course, if you have a cocycle phi, okay, and you know that that cocycle is a coboundary, then automatically you will have that the Birkhoff product along periodic orbits, this is a periodic orbit of period n, the Birkhoff product will be equal to the identity of the group G, because you have this property here, and this is the same point. Okay, so a necessary condition to be a coboundary is that the Birkhoff product along every periodic orbit should be equal to the identity. Okay, and well, we can revise the main question, asking, okay, there are some other obstruction. We have the periodic orbit obstruction, and there is something else. And moreover, another natural question is, what's the relation between the regularity of phi and the regularity of u, where u is the solution of the cohomological equation? Okay, I will write here the cohomological equation. We are asking if this holds for every x n. And so we are trying to solve this cohomological equation. We are trying to find a solution u. And the question is, well, if we can solve this equation, which is the regularity of u comparing to the regularity of phi. Okay? And so the first result about the cohomological equations of hyperbolic system is due to Livsic, who said that if you have a transitive hyperbolic homeomorphism, your group in this case is R. So this is the first, of course, natural example. And you have so a real cocycle, and here the regularity is very important. In general, there is no nice theory of cohomological dynamics in the continuous category. I mean, you can work with just continuous dynamical system, but in general, the cocycle should be more regular, because well, in the continuous category, there is some very common pathologies, and you cannot have a very good description of this. Essentially, the result of Livsic said that the periodic orbit obstructions are the only one that appear in this case. That means that you can solve this equation if and only if the Birkhoff products along any periodic orbit is the identity of in this case, it's just 0. Okay? Because we are working in R. This is for any P fixed point of Fn, and of course this for any n in Z. Okay, this is the classical Livsic theorem. And well, about the regularity of the solution of the cohomological equations, there are some results of, well, the first one of Livsic itself. Essentially, first he showed that the solution of the cohomological equation is continuous, but a posteriori it is held also. Using Fourier analysis techniques, he showed that if you have a hyperbolic automorphisms of TD, of the d-dimensional torus, and your coboundary, and your cocycle phi is C infinity, it's not only Helder, but C infinity, then the solution is also C infinity. As I said here, since this is a very homogeneous dynamical system, you can apply Fourier analysis techniques. And, well, it's not very complicated to show that the solution is always C infinity, so you have sort of rigidity in this case. Also using theory, not only Fourier analysis, but, well, the generalization of Fourier analysis, which is representation theory, Guillemin and Kashdan showed an analogous result for geodesic flows on surfaces of constant negative curvature. The geodesic flow on such of Riemannian surfaces are also Riemannian surfaces are also homogeneous flows. So it's also possible to apply harmonic analysis techniques, in this case, representation theory. And finally, in the 80s, Rafael de la Llave, Marco and Morillon, they show the general result for arbitrary C-infinity anosoph diffeomorphisms. That means if you assume that F is a C-infinity anosoph diffeomorphism, your cocycle is also C-infinity, then, and of course satisfy the periodic orbit obstruction condition, then automatically the solution is also C-infinity. So you have a very strong rigidity for cohomological rigidity for such systems. Okay? Well, let me mention very basic idea of how to Livsic prove it, because we will use these ideas for our theorem. The idea is the following: you take the cocycle and you consider the skew product. You define the skew product in this way, and you notice that if the cohomological equation written in this way admits a solution, then the graph of U should be f hat invariant. Okay, this is very simple. Observe that here you have the graph of U here, and any translate, in fact, not only the graph of U should be invariant, but any translate of the graph, it's also invariant. So you have your product manifold, your product space here completely foliated by the invariant graph. Okay, and in fact this is an if and only if. I mean, if you can construct those leaves here, then those are the graph of the solution that you are looking for. And so the idea of Livsic is to take a point here, an arbitrary point here, for instance, this red one here, and start to iterate with f hat and try to see if the orbit of this point generate the leaves that the graph that you are looking for, okay, of the function that you are looking for. So you take a point with dense orbit, you define U of x equal to 0, you define U along the orbit in such a way to guarantee that this is in fact a solution of the cohomological equation, at least on the orbit. And the question is, okay, you have U defined on a dense set, and the question is if you can extend this to the whole space M. And the answer is yes, and this is essentially contained in the Anosov closing lemma. The idea is that close to you want to see what happened when you have x here. You start to iterate, and you come back here, fk of x. And this means, and the annals of closing lemma said that here you have a point P, which is periodic. You return here. And remember that the Birkhoff sum along periodic orbits is equal to 0. This is the periodic orbit obstructions. And that means, this is the picture that we have here. We have a point fn of x. We have another iterate which return close to that point here. And when you look in the skew product, you want to see if this could happen, that this is the red point. After kth iterate, it returns here kind of far away from the original point here. And this, of course, should be an obstruction for extending extending your function u to the whole product space. But this cannot happen because the periodic orbit obstructions implies that this point here is periodic. This point here is periodic. Sorry, here this should be p, not x, p. Okay? And this is a periodic point for f hat. And so this cannot happen, that this return close far away, because the yellow point return to itself. Okay, this is a very simple idea of Livsic theorem. Okay, so the question is, what happened with more general groups? For locally compact groups, for instance, or yes, let's start with locally compact groups. Well, Livsic himself, he showed that, it's just a remark, that if your group admits a bi-invariant distance, then the whole proof works well, and you can use exactly the same proof. But it's extremely important that the distance is bi-invariant. Okay, and the very same idea works well. In a year later, Livsic also shows the case for Lie groups, okay? But this is not the general result, because it's a kind of perturbative result. I mean, you have your cocycle phi, which is not very far away from being identically equal to the identity of the Lie group. And in this case, if your cocycle is close enough to the identity and satisfy P, the periodic orbit obstruction, then it is a coboundary. And essentially, the idea is that if you have an arbitrary Lie group which does not admit a bi-invariant distance, when you are rather close to the identity, you have certain control of the distortion of the distance. When, I mean, you start with the left invariant distance. When you multiply by the right, you change the distance. But being close to the identity, you have certain control of the distortion of the distance. So that's essentially the idea of the proof of Livsic. And the global version without any localizations appeared 2 years ago in a paper in Annals. It's a paper of Boris Kalinin. He proved the global version of Livsic theorem without any localization assumption for the general linear group. But essentially, the same idea works for arbitrary Lie groups. Okay, so the case of, when I say arbitrary Lie groups, are finite dimensional Lie groups. Okay? And in a certain way, this is the very general, the first general result for groups who doesn't admit bi-invariant distances, okay, without any localization assumption. Okay, so what about group of the infinite dimensional groups? Okay, in dynamics, the most natural example of infinite dimensional groups are groups of diffeomorphisms. So you can ask yourself, what happens if you have a cocycle taking values in group of diffeomorphisms? Is it true Livsic theorem? Well, the first result in this direction, it's a result due to Nitsika and Turek in 1995. And, well, you have transitive annals of diffeomorphism. X is not an arbitrary manifold, but it's a manifold that embeds nicely in Rn. It's a technical hypothesis, not very important here. And if you have a Kölder cocycle with R bigger than 4 and satisfy the periodic orbit obstruction and a certain localization, which is here, it's very important that this is the CR distance from any diffeomorphism. This is for every P to the identity. Then you have that phi is a diff R minus 2 coboundary. That means that in this case, your solution U takes values in R minus 2. This is it's not a big issue because I don't remember exactly, but about 5 or 7 years later, Nitsika and Turek themselves, they showed that there is no loss of regularity here. So this was the original statement, but right now we know that there is no loss of regularity at all. Well, what else? So this is the version of cocycles taking values in group of diffeomorphisms with the localization assumption, okay? This localization assumption was changed by Rafael de la Llave and Alistair Winstor in 2 works, in 2008 and 2010. They changed it. The localization hypothesis of them is much better than the Nitsika and Turek for C1, but it's not very good for instance, no, it's not good, no, it's terrible for C infinity diffeomorphism. It's completely terrible. But it's much better for C1. But it's also a local theorem. In a certain way, you are not very far away from the constant to the constant cocycle equal to the identity. And a global version of Livsic theorem for infinite dimensional groups is due to Andres and Mario. And the only problem is that this group here is not exactly in our setting because this is not a metric group. So the topology of the group of charms fixing the origin in C, and it's not exactly a metric group. But nevertheless, it's very important to remark that this is a first result, global result for infinite dimensional groups. Okay? And so our result, well, I didn't mention, but it was in the first slide. This is a joint work with Rafael Potri from Uruguay. And, well, our result is the first global result for a group of diffeomorphisms. Here is where the low-dimensional manifolds appear. We show that for C1 diffeomorphisms of the circle or C1 diffeomorphisms of surfaces preserving a measure, an area form. In this case, if you have a transitive hyperbolic homeomorphism and you have a Kölder cocycle, then you have the Livsic theorem globally without any assumption about localization, the global theorem. Okay? So, and invoking the results of Nitsika and Turek that I said that they improve the regularity of the solutions of such cohomological equations, you can show exactly the same result for CR diffeomorphisms of the circle and of surfaces. Of course, if we were able to show this result for any other group of diffeomorphism, the same holds here for higher regularity because the result of Nitsika and Turek is very, very regular. It's very very general. Okay? So this is the theorem. And well, I want to explain some of the ideas of the proof. The main idea of the proof works for any manifold. It's not necessary to work in low-dimensional manifolds, but only at the end will appear the restriction of the dimension. So for the time being, let's suppose that X is an arbitrary smooth manifold. G is a group of C1 diffeomorphisms. And of course, we consider the skew product. In this case, we use M times X, not M times G, like is usually used in Livsic theorems. And well, you can define the Fiber-Lyapunov exponent. The Fiber-Lyapunov exponent is simply you take the skew product and you consider the norm of the derivative along the fiber. Okay? In this case, we don't have any smooth structure on the base, but we have smooth structure on the fibers. You take the norm of the derivative on the fiber, and you define the upper, the biggest and the lowest Lyapunov exponents along the fibers. Okay? This will play a key role for us. And we use this notion, which is, of course, it's a very natural notion of domination. I mean, at first when you read the works of De La Llave, Nietzsche, Törer, they use the localization assumptions are in certain way, certain hypotheses are some kind of domination. But in general, they are much more stronger than just domination. This is the simplest notion of domination. This is the most natural notion of domination. And we will see that this is, in fact, much weaker than the localization assumptions that they use, but this is enough for Livsic theorems. And so the main idea, the main result to prove the Livsic theorem for groups of diffeomorphisms is the following. We will assume for the time being that phi is Lipschitz, not only Hölder, but Lipschitz. This is not a main issue because when you have a hyperbolic homeomorphism, you can change the distance of the metric space in such a way to make phi not only Hölder but Lipschitz, and it continues to be hyperbolic with this new metric. There is a little issue about the domination, but this is not a big problem in our setting. So we will assume that phi is Lipschitz, satisfy the periodic orbit obstructions, and so the following three statements are equivalent. This is the statement of the theorem. The first one said that all Lyapunov exponents with respect to any invariant measure vanishing. Okay? All are equal to 0 for any invariant measure that you consider. Of course, remember that these Lyapunov exponents are the Lyapunov exponents along the fiber of the product. Okay? This is equivalent, the vanishing Lyapunov exponents is equivalent to the domination of the cocycle with respect to the homeomorphism. I mean, in our setting, of course, this is very, very important, the periodic orbit obstruction. We are assuming periodic orbit obstruction in this case. And these two statements are equivalent. And the most interesting for us is that both conditions are equivalent to phi be ecoboundary. So if you have any of these conditions, you automatically will be able to solve the cohomological equation. So I won't prove the equivalence between everything because the only thing that I'm interested is in showing the 1 implies 2, 2 implies 3. because we will show that these conditions for low-dimensional manifolds are satisfied. Okay, and this is the idea of the proof. The idea that the vanishing of Lyapunov exponents imply domination is it's rather classical, rather standard. You suppose that it's not dominated, then you can find sequence of natural numbers going to infinity, points satisfying this. This is the derivative along the fiber, x. You are supposing that you are violating domination. You take an accumulation point of the measure. This will be an invariant measure for f hat. And it's not completely, it's very easy, but it's not completely trivial to show that for such a measure mu hat, you have that the Lyapunov exponent of the measure should be bigger than lambda. By the subadditive ergodic theorem, you will see that there are certain points with Lyapunov exponent bigger than lambda, and this contradicts your assumption that all Lyapunov exponents are 0. So this is rather standard, rather classical. Okay? So let's go to the most important part of the theorem, which is we will show that domination implies that phi is a coboundary. To do this, the first step consists in constructing invariant foliations for the skew product, okay, for f hat. You have that f admit invariant foliations, well, they are not exactly foliations, they are laminations because you are not working with in a differentiable manifold. A priori M is not a differentiable manifold, but this is not important. And the idea is that under the hypothesis of domination, you have that f hat admits invariant foliations because it's essentially a partially hyperbolic system. It's not exactly because you don't have differentiable structure on the base, but you can construct using the graph transform, you can construct invariant foliations for f hat. That means this is for the product. And those manifolds here are in fact Livsic graph over the ellipse of f. Okay, this is rather standard. And using these foliations here of f hat, we will show that we have essentially the same, we can apply these ideas of Livsic of extension along orbits. Okay, in the following way, using this foliation, you can show that whenever you take a point in the product m times x, and you consider the closure of the orbit, then that closure is a graph of a function, of a continuous function over the closure of the orbit on m. So whenever you have a skew product, you take a point, you start to iterate that point with f hat, and in this case, always the closure of this orbit is always a graph. So, and this is essentially the idea of Livsic of defining the solution, constructing the graph, and taking a point with a dense orbit. This holds for any point. Okay? And the idea is very simple. It's essentially the Anosov closing lemma, but taking care of the foliation of the skew product. Okay? So remember the Anosov closing lemma said that you have a point x, you have f kate of x that returns close to itself. You take the point p, which is a periodic point, okay, and the period of p is kate, so p is equal f kate of p. And essentially you are considering y is the heteroclinic point. This is the bracket, yes? Y is the bracket of x and p, the brackets of the local product structure. So you have those points here, x, y, and p. This is a relation. Essentially, they move together. This is the only important thing for us. They move together and they don't separate till the time k. And so in the skew product, you do the following. you take, initially you take, this is the point xt, okay? With xt, you go along the holonomy of the unstable manifold, and you go to ty, which is the intersection of this manifold here with the fiber over y. And from here, you move along the holonomy of the stable manifold, the stable holonomy. And so you have these 3 points here. And the idea is the following. In the base, they move together till time k. Yeah? On the fiber, they will also move together because they belong to invariant foliations. And so these 3 points will move together till time k also. And on the other hand, the periodic orbits obstruction said that this point here, which is the coordinates of this point are PTP, is a periodic point for the skew product. This is the periodic orbit obstruction. So that means that this point here returns to itself, and of course this point should return close to itself. Not exactly, but close to itself. And this is the idea how to prove that the orbit closure is in fact a graph. Okay? So now you have that for every point, you take the orbit closure, and this is a graph. Now you fix a point x0 such with dense orbit. If you want, you can take a positive dense orbit. Okay? And you will fix x0, and on each point, you take x0, and on for each point of the fiber over x0, you will define a set V, which is the graph of the function vxt. Okay, this function here is a function such that the graph of this function is the orbit closure of the pair x0 t. Okay? And the idea is that those sets here are saturated by the stable and unstable manifolds of the skew product. And automatically this implies that those sets here gave a foliation for an invariant foliation for the skew products. And in fact, the leaves are Lipschitz. Essentially, what I'm saying here is that these leaves here are nothing but WSU leaves, in the following sense that the two foliations are, how you say, mutually integrated. It can be simultaneously integrated, and essentially those V are exactly the WSU leaves. So it's a very particular skew product. So, of course, this is a straightforward consequence of this, because you know that these invariant manifolds are leaves. How you prove it, this result, how you prove that those sets here are saturated? Well, you use the topological invariant principle of Arturo and Marcelo. The statement is rather technical, but in our case, we have all the hypotheses satisfied, because you should have something downstairs in the base which admits local product structure in such a way that there exists measures with local product structure. I don't want to enter in the details of this, but these SU holonomies are exactly the holonomies along the W hat stable and unstable manifold that we have. You know, we know that every Lyapunov exponent along the fibers vanishes. This is the original hypothesis. I said that domination and vanishing of Lyapunov exponents are equivalent. So in this case, we have here. And in this case, this is completely trivial because we have an invariant measure which is just a delta about each point. So in the base, you take a measure with local product structure. And in the product, you take exactly the same measure, taking a point on each fiber, which is exactly a point on the graph of B. So this is obviously satisfied. And the conclusion of the theorem, the conclusion of the theorem is that these disintegrations are SU invariant. In our case, that means that, in our case, that means that the set V are saturated by the manifold, because we have only one point on each fiber. So this is a very straightforward application of the invariant principle. Okay, so we are in a very good situation, because we know that now the stable and unstable leaves of the... Sorry? That you disintegrate, okay? And you take the disintegration here on the fiber, and you push along the holonomies. Well, the push of the disintegration coincides with, yeah. And in this case, it's very straightforward, yeah. So we are in a very good position, because we have that the leaves of the stable and unstable manifolds are simultaneously integrated, and so you have something very, very similar to the Livsic picture that I draw in the first case. You have the foliations, and you would like to use those leaves to define the solution U. Okay? So we are almost done. We do the following. To define U, you say, okay, U will be a map from M to the group of C1 diffeomorphisms. You define that on X naught, this is the identity of the manifold X. And to define U of Y, for instance, the only thing that you do is you take the point T over X naught, and you define U, Y of T as the intersection of this leaf here with the fiber. This is essentially what I'm saying. I'm fixing the identity on the point X naught, and on the other points, I'm defining this just along the holonomies. Stable or unstable holonomies, because we know that they live in the same, they stay in the same leaves. Okay? And in this way, you define this U. But there is an issue here. I'm saying that the diffeomorphisms are C1. We know that the leaves of the foliation are Lipschitz, but for the time being, I'm not saying nothing. I didn't say anything about the holonomies of B. The regularity of U will depend on the holonomy of the W hat SU foliation. Well, to prove that the holonomies of B are smooth, we do the following. Now you fix T, X naught T, and you will define a cocycle in this way. Here I'm cheating a little bit, because I'm assuming that the fiber bundle, the tangent bundle to the manifold X is trivial, but this is not a big issue. So in this case, you can assume that this is the general linear group. And here, on the point X, I'm considering the intersection of B with the fiber. And here, I'm considering the derivative along the fiber. Here, D is the dimension of X. This is the dimension of X. So I'm taking the point here. You have a diffeomorphism here. And what I'm considering is the derivative along the fiber at this point. Okay? And this will be represented by a matrix. Yeah? And the interesting point of this cocycle here is that it satisfies, it's Lipschitz, it satisfies the periodic orbit obstruction. Remember that whenever you have a periodic point, you return to the identity, so the derivative, the product along the derivative will be the identity. And moreover, so it's Lipschitz, it satisfies the periodic orbit obstruction, so you can apply the Kalinin-Lipschitz theory to show that this cocycle here, that is a cocycle of the derivative is in fact a coboundary. And using the fact that this cocycle is a coboundary, you can show that the holonomys of the foliation is in fact smooth. And essentially, this will show the change of coordinates. How would you say? In a certain way, it's a change of coordinates when you take the holonomys along the leaves. So the fact that this cocycle is in fact a coboundary is crucial to prove that the holonomys are in fact C1. If the holonomys are in fact C1, that means that your U here is in fact, the image of U is in fact in diffeomorphism, C1 diffeomorphism. In other case, the image of U would be here only on homeomorphism of X. But in this case, the image is in the group of C1 diffeomorphisms. So we are done. We are done for theorem 1, who said not exactly the equivalence. I didn't show the complete cycle of relations. But we are almost done because we show that the vanishing of the Lyapunov exponents is, believe me, is equivalent to domination, and domination is equivalent to the ecoboundary. But I said that theorem is only true for, well, no, sorry, it's not only true. We know how to prove it in the case that X is a circle or a surface, and in the case of surface, it preserves an area form, okay? And why this is important for us? Because so far we don't know if the periodic orbit obstruction implies that the Lyapunov exponents along the fibers are equal to 0 for any invariant measure. We don't know. In the particular case, in those cases here, we know that this is true. And that's the reason why the theorem holds. And the idea is that if you have a measure, mu hat, which is invariant, and in such a way that the Lyapunov exponents, sorry, this is mu hat. These Lyapunov exponents are not equal to 0, and assuming that you are in this situation here, the measure mu hat would be something like a hyperbolic measure, okay? I mean something like a hyperbolic measure because we don't have differentiability on the base, but essentially you have a hyperbolic behavior on the base, and if you have a non-uniformly hyperbolic behavior on the fiber, then you are in a situation of a non-uniform hyperbolicity, of non-uniform hyperbolic homeomorphism in a certain way. And well, suppose that you, using the Katok closing lemma, you could prove that there is hyperbolic periodic points. Of course, in this case, you cannot apply Katok closing lemma because you don't have enough regularity, especially on the base. But using an argument a Laplace, you can reprove Katok closing lemma in this setting. And this would imply that you should have a hyperbolic periodic point for the skew product. Essentially, this hyperbolic periodic point, the only point that it's interesting for me, that this should be an isolated periodic point. But the periodic orbit obstructions, does not allow to have isolated periodic points. Whenever you have a periodic point for the skew product, yeah, the whole fiber is periodic. So there is no hyperbolic, there is no isolated periodic point. So in this case, we could reprove Katok closing lemma, showing that there are isolated points, and this is impossible. The question, of course, is if this condition holds for arbitrary manifolds in any dimension, because, of course, this argument, well, in higher dimension doesn't hold. Sorry?
This argument that you have in low dimension to be isolated periodic point is for the circle.
The circle, yes, but if on surfaces assuming, yeah, exactly, assuming area preserving. Yeah.
Because you have positive lepton exponent in the surface, one negative.
Yeah.
You have a kind of forces phenomenon.
Of?
Forces on the surface.
No, sorry. When I say it isolated, I'm isolated with fixed period. Fixed period. You know? No, of course. No. Yeah, thank you, Enrique. No, when I say isolated, it's the fixed point of fk. The fixed point of fk are isolated. Yeah, exactly. Just thank you. No, yeah. No, because it's essentially as I said, it's a reconstruction of cutoff closing lemma proof. So, and it works. The only important point here is that you have all Lyapunov exponent different from 0. But yes, this isolated mean for a fixed period. And the periodic orbit of structure, whenever you have a period, if you have in the base period k, on the fiber, you have period k for every point on the fiber.
But for you, S2 is not the sphere.
No, this is any surface. No, in fact, I wrote S before, but I said, no, I want to make clear that, yeah. It's any surface, yeah.
Do you think like larger dimensions? You can work like instead of diffeomorphism, you actually get only diffeomorphism at the central dimension.
Or simplicity, I don't know. But of course, this is the question, the next step. This should be interesting to know if this is true in any dimension. Okay, thank you very much.
Any more questions? Well, thank you so much.
Okay.